Our topic in this video is the mean value theorem. Now, by itself, the mean value theorem on the surface could almost seem like it's a piece that may be intuitively obvious. It may be a piece that when you first look at it, you say, well, so what? What is that good for? The mean value theorem is going to serve as the foundation that explains why a lot of our upcoming topics are true. This will be an incredibly important tool to help us develop other techniques which have a broader base for being able to have uses. Our learning objectives are fairly straightforward. You should understand Rolle's theorem and the mean value theorem, and then be able to apply those theorems to prove or explain some characteristics of functions. So take a moment, pause the video, write down Rolle's theorem. All right, so you've written down the theorem. Obviously, you've read it since you had to write it down, but what is this thing really saying? What's going on? Whenever you read a theorem, you would like to be able to say, okay, we have all these givens. If this stuff is true, then I can make this conclusion. Well, when we're looking at this, we are being told, first of all, we have a function over some interval, a closed interval, from A to B. We are also told it is a differentiable function. Since it is differentiable, we know that there are no holes, there are no gaps, there are no sharp corners. It's something smooth. The third condition tells us f of A equals f of B. So at the endpoints of this piece, we would have something that says, here's f of A, here is f of B. So basically, well, I drew that one a little bit too high. We have 2 points that are on the same flat line. There's f of A, there's f of B. Basically, if we had to start filling in the gaps, we've got to connect the 2 points and make sure it's a continuous function and make sure it's a differentiable function, so it's a smooth drawing. Well, you'll agree that there are a couple possibilities. I could potentially have it be a horizontal, just a constant function, in which case, here's a point C where the derivative is equal to 0. Well, that one's kind of boring, right? Or potentially, I could have it go upward and make its way back down. Well, if that happens, here is a point with an x value of C where the derivative is equal to 0. Or even if it went underneath, there is somewhere where the derivative is 0. That's Rolle's theorem. Intuitively, you look at the graph and it seems really, really obvious. Our textbook goes through and marches through the explanation with an algebraic proof of this. Well, this is a piece that we are going to use to just say something like here. Fry shoots a free throw, and because he's terrible at basketball, he airballs it. And it lands directly in front of the rim. Why does Rolle's theorem guarantee there's a point where the velocity is 0? Well, here's the big thing to keep in mind. We've got Fry. We have basketball hoop. If we got Fry shooting the ball, and it's going to follow a path, airballing and landing in front of the rim. You will note we have continuous, we have differentiable on this interval, and there is a point when the ball goes up and when the ball goes down where it has the same height. Rolle's theorem guarantees us there is a point at the top where the derivative is 0. What is the derivative of a position function? Velocity. Because the derivative is equal to 0, it tells us the velocity is equal to 0. kind of a cool little physics piece, but there is a very, very brief moment in time when you shoot a basketball, when it reaches the apex, it's actually not moving at all. For an instantaneous moment, less than a millionth of a second, for a very brief moment, it's not moving at all. It's just floating in midair for a ridiculously small period of time. Instantaneously, it's not moving at all, which is kind of a cool thing to think about. You chuck stuff up in the air and it stops in midair until gravity pulls it back downward. That is a consequence of Rolle's theorem. Okay, so this one, getting back to some algebra, prove that the equation x cubed plus x minus 1 has exactly one real root. Well, if we're going to prove it has exactly one real root, it would make sense that we should say it has one at all. That's where we're going to use the intermediate value theorem. Do you remember what the intermediate value theorem tells us we need? That's no, you're thinking of the squeeze theorem. The intermediate value theorem says, first off, if we have a continuous function on an interval from a to b, well, this is a polynomial. Polynomials are continuous everywhere, so definitely on an interval from a to b. And we have, and I'm going to rewrite the intermediate value theorem so that it's specific to a root. If we have one of these values, f of a or f of b, that's less than 0, and one of them that is greater than 0, if you get these three things, then you know that there's some number in between a and b that will give you the actual function value of 0. Now, the intermediate value theorem actually says it's any height in between f of a and f of b, but we're using specifically 0 for this problem. Well, give me an x value that's going to make the whole thing negative. How about -1? If we try -1, that would be -1 plus -1 minus 1. So that would give us a height. F of -1 is 3. I'm sorry, -3. And if we tried +1, 1 plus 1 subtract 1 is +1. So if we plug in 1, we'd get a height of 1, which is greater than 0. So we have identified this is a function that is continuous from -1 to 1. And one side is less than 0, the other side is greater than 0. So by the intermediate value theorem, there has to be a number somewhere between -1 and +1 that's going to give us a 0. That's what this stuff in purple is. So this is the work that would say the intermediate value theorem gives us a root. Well, the intermediate value theorem says there's at least one root. There could possibly be more. So we know one of them exists. Well, if we're going to try to prove that there is exactly one, then we should actually go through and say, if it's exactly one, to show that it is exactly one, we would need to demonstrate that there can't be more than one. Okay, so if we assume that there's more than one and show that it's wrong, then we know that there's exactly one. Well, if we assume that there are two of them, if we assume that there are two roots, then that would be telling us we've got like an f of a that's equal to 0 and an f of b that is equal to 0. Rolle's theorem then, and this a and b we're putting at like -1, +1. If we are making this assumption then, we have continuous, we have differentiable, so we have f of a equals f of b, they both equal 0. Okay? then what this is telling us is there must be somewhere with the derivative is 0. Okay, Rolle's theorem would guarantee the derivative must be equal to 0 somewhere. Okay, does that make sense? But let's actually look at the derivative. If we take the derivative of this piece, we would have 3x squared plus 1. Can the derivative equal 0? If we tried solving this, we would have x squared equals negative 1/3. Can you take the square root of a negative? No. So, Rolle's theorem would guarantee there must be somewhere where there's a derivative of 0, except it can't happen, which tells us our beginning assumption has to be wrong. There are not 2 roots. So if the intermediate value theorem gives us 1, and contradicting Rolle's theorem says there's not more than there can't be 2, then that lets us know right away there's exactly 1. Does that make sense? Okay. Pause the video, write this one down. Okay, so what is this thing actually saying? What's going on with it? Well, once again, let's look at the assumptions of the theorem. The assumptions will tell us what we need, and then the conclusions tell us what we get. So, once again, we have a function that is continuous on a closed interval. So from A over to B, we know no holes, no jumps. It is differentiable on the open interval. Okay, because it's differentiable, we know we've got smooth, something, no sharp corners. So it's telling us if we have something that looks like this, f prime of c, there is some number in between a and b where the derivative is equal to f of b minus f of a over b minus a. I invite you guys to tell me that should look familiar. What is that? F of b minus f of a over b minus a. If we took the limit, we get the derivative. But in general, without having the limit, this is the average rate of change. Average rate of change, remember, is the slope. This piece over here is the slope of the line between A and B. We could very easily, with numbers, look at this piece and get a number m. What this theorem tells us is that somewhere there is a point C with the exact same slope, so that the derivative at that point will be parallel, or the lines will be parallel. Does that make sense? And you'll note, it's possible that there could actually be more than one. The mean value theorem guarantees there's at least one spot where the instantaneous rate of change is equal to the average rate of change. That's why it's called the mean value theorem, because the average rate of change is the mean rate of change. Okay, so let's look at this and see specifically how does this thing get used. How does the mean value theorem look? Well, we've got our interval from 2 to 5. Again, it's a polynomial, so it's continuous, it's differentiable. What is f of 2? What is f of 5? Okay, so 2 squared plus 2 is 6. 5 squared plus 5 is 30. We could then put this stuff together and say the slope between these, f of 5, subtract f of 2, over 5 minus 2, 24 over 3, it tells us the slope is equal to 8. Well, I would like to have an equation of the line then. We know that the slope between the 2 points is 8. In order to have the equation, we could have y minus y1 equals slope times x minus x1. And we could just, I'm sorry, why did I write 5? But it's the y value from f of 2, that's 6. Here's our x1 and y1. So anyhow, by taking plus 6, we could rewrite the equation this way and have something that we could type into our calculators. Now I'd like to be able to do the graph in effort of saving some time. Put it into the graph, and here's what we saw. You'll note the window goes from -2 up to +10, and from -5 up to +40. If you would like to create the exact same window that I have, here's how I did it. Well, here's just our function x squared plus x. Also went through and put in that line that we just figured out. You will note then, we've got the line sitting here, and I want to make it thinner, and I'll use yellow because I was using yellow in the previous ones, and say here is our point, our line. The mean value theorem guarantees us that if I drag this outward, there's going to be somewhere where we get a tangent. Yep, that's what the mean value theorem guarantees us. Well, the big question then is, where is it? Where is this point? We could take the derivative, get 2x, f prime of x, I was getting ahead of myself, is 2x plus 1. By the mean value theorem, we know that there's somewhere where the derivative is going to match the average rate of change. So if we have f prime of c equals 8, then we have that. Because if we plug in a constant here, we'd have f prime of c equals 2c plus 1. F prime of c, we could figure out where it is. Well, subtract 1, divide by 2, and not only do we know where it is, not only do we know that it exists, we actually know where it is. This is the x value. At x is 1, 2, 3, 4. At 3.5, we would be able to come straight up and say right here, that's where we have this tangent that is parallel to our secant line. That's the mean value theorem. There is some tangent line that will be parallel to the secant line. Intuitively, that should kind of make sense, because remember when we were doing our tangent, how we talked about the limiting process, how you drag it closer and closer and closer until there's only one point? The mean value theorem gives us a tool for possibly finding where that one point is. Now this is a piece that I said before, it's really important to understand, so here's the question. What's the connection between the average rate of change and the instantaneous rate of change? Not equal each other everywhere, but the mean value theorem tells us there's somewhere, some point somewhere, where the average rate of change equals the instantaneous rate of change, which would give us our parallel lines. So, last problem we've got. Before we begin it, one of the big uses behind the mean value theorem, the mean value theorem can allow you to figure out stuff about the function when you just know information about the derivative. So specifically, we have f of 3 is equal to f of 0 is equal to 3. Okay, so 1, 2, 3, we've got that point. And we know f prime of x is greater than 5 for every single value of x. Well, if the derivative is greater than 5 for all values of x, then it tells us if this is a slope of 5, we can never slow down. We're always going up at a faster rate than this one is. Well, if we are forced to go up at a faster rate, we would also then have 1, 2. What's the smallest value that could possibly be? We don't have an equation for f. We don't have any knowledge about it, but the mean value theorem will allow us to figure out what's the smallest possible height for that. In particular, you notice that we're looking at the mean value theorem requires that we have a continuous function. We're not told that we have a polynomial. That's kind of been our go-to move so far. But we are told the derivative is greater than 5 for all values of x. Well, if the derivative exists, we know the function has to be continuous. That was one of the theorems that we were looking at previously. In order for the derivative to exist, remember there's no sharp corners, there's no holes, there's no gaps for the derivative to exist. Well, at the very least then, that tells us no holes, no gaps. No holes, no gaps is continuous. So this piece will allow us to know it is continuous, and it also tells us it's differentiable. So when we're looking at the mean value theorem, we have continuous, we have differentiable. We've met the assumptions, so now we can make the conclusion. We know that there is somewhere where f of 2 minus f of 0, this must be true. Well, you'll note then this would be just the number 2. So we could multiply by 2. And if we multiply by 2, then that would tell us 2 times f prime of c is equal to f of 2 minus f of 0, which was 3, which would allow us to say plus 3 on both sides. And so we get this piece that says f of 2 will be equal to 3 plus 2 times f prime of c for some number c. We have no idea which one. But we do know this derivative is at least 5 for absolutely everything. If it's 5 for absolutely if it's bigger than 5 for everything, it has to be bigger than 5 for this c. Like when we were doing our epsilon delta definitions, this is a piece that we know is less than or equal to 5. So if we've got this piece that's bigger than 5, when we do a substitution, that tells us this piece has to be bigger than 3 plus 2 times 5. It's similar in concept to our epsilon delta substitution at the end. If you substitute a smaller number, then it's going to be bigger than the substitution. So crunch some numbers. 3 plus 10. This height has to be at least 13. No other way around it. We have no equation, we have no graph, but we still know that this height is bigger than 13. The question was asked, could we make this f of 2 equals 13? We would not know that because when we were doing the substitution, if this derivative was actually 6, then what we would wind up having is the derivative would be equal to this piece, and that winds up creating some issues. Basically, when we wind up doing our substitution, this inequality was not an equal sign. Because it was not an equal sign, it does not allow us to make the conclusion that it's equal. So there we go. Do you understand Rolle's theorem? Basic idea is if you've got continuous and differentiable, hey, it has to turn around and be a horizontal line for our tangent. Mean value theorem. You've got continuous and differentiable. There has to be somewhere where the tangent line is perpendicular to the secant line. Understand those two facts and be able to apply the equations to figure out some characteristics of functions. That's all we need.